Right, so in today's lesson, we're going to look at a couple special cases. You might have heard it before. One is going to be the difference of squares, and the other will be perfect squares. So to see difference of squares, factoring by difference of squares, let's first look at some examples, and we're going to expand them. So these examples all have something in common. We have x plus 3 and then x minus 3. So the second bracket's the same as the first, except we have a negative in for the second term there. Right? Same here, 2x plus 3, 2x minus 3. 3x plus 5y, 3x minus 5y. So if we expand this one, we're just going to FOIL it, right? Like this. So we get x squared minus 3x, same here, 3x, and then 3 times negative 3 is minus 9. Okay, our middle terms are like terms, so we can simplify them, and 3x plus 3x, well, that's just 0. So we're just left with x squared minus 9. Okay, so there's kind of a pattern there. And when we have patterns, we can come up with these almost like little tricks or shortcuts. Let's try the second one. Because this pattern looks like all I have to do is take 3 squared and make it 9, and x squared and make it x squared, and then we just throw in a negative. Let's see if that works for the next one. So 2x times 2x is 4x squared. 2x times 3 is plus 6x. Then minus 3 times 2x, minus 6x. And then minus 3 times plus 3, minus 9. So again, our middle terms are canceling. And we're left with 4x squared minus 9, which again looks like all you do is square the first term and square the second term and subtract. So knowing that pattern, I could look at this and say, oh, 3x plus 5y, 3x minus 5y, that's the difference of squares. I don't have to do all this foiling or extra work. I can just do, well, 3x multiplied by itself is 9x squared. Subtract, and then 5y multiplied by itself is 25y squared. Okay. It takes time before you'll be able to recognize that something's a difference of square and then just write it in one step. It is good to know. It's almost like when you first started to learn how to type, you were probably a lot slower than actual writing. But with practice, you would have become a lot faster at typing. So now we're going to use this this identity, this special case of difference of squares, which can be written with this formula here, to instead of expanding, we're going to go backwards, and we're going to factor. So this looks like it might be a difference of squares. Right? We have a p squared minus a 9. And a 9 is just the square of 3. That's a perfect square. So I can write p plus 3, p minus 3. Okay? That's what it looks like it would be. If we're not sure, we could always expand this and think of it as p squared plus 0p minus 9. And we can ask ourselves, what two numbers multiply to give us minus 9 and add to give us 0? So in this case, it would be 3 and minus 3. So yeah, it works. This is the way we did it yesterday, but now we're just using the idea of a difference of squares to do it this way. Now this one, at first glance with this one, you might think, is this a difference of squares? Well, 36, yeah, it could be. And 10, it could be. But to make things a little easier, remember what I always said, check to see if there's common factor first. And in this case, there is a common factor, 4. So we can pull out a 4. Right, 4 goes into 36 9 times, and 4 goes into 125 times. Right, so we're just going to leave that 4 out there. 9 is a perfect squared, right? 3 squared is 9. So let's have 3m. And 25 is a perfect squared, right? 5 squared is 25. So we can have 3m plus 5 and 3m minus 5. There you go. So I'm going to pause there. I want you to... So first I pulled out the common factor, just to explain it again. And so 4 times 9 gives us 36, and 4 times minus 25 gives us minus 100. And then we can look to see if it fits with this formula. This formula says something squared minus something else squared is going to equal, like a squared minus b squared is a plus b and a minus b. But that a has to be a perfect squared. Right? So for example, if you had 10, what number multiplied by itself gives you 10? That's not a whole number. I mean, if you went on your calculator and you did, well, the square root of 10, right, it's 3.162277766. So that's not a perfect squared. But 9, on the other hand, 9 is a perfect squared because it's perfectly equal to 3 squared. Right? Similarly, 25 is also a perfect squared because it's equal to 5 squared. So when I look at these two numbers, I ask myself, are they perfect squares? In the case of 9 and 25, yes, they are. 9 is 3 squared. Right? We're not writing squared because when we factor it into two binomials, you can then expand it, and 3m times 3m when you FOIL will give you 9m squared. And then is 25 a perfect squared? Yes, it's 5 squared. So then we just write 3m plus 5, and following with the formula, you do 3m plus 5 and 3m minus 5. And you can get this. Right? If you're still unsure with yourself in the beginning, again, you can expand this to be 9m squared plus 0m minus 25. And then you can use decomposition, which we went over earlier, to factor that. And you would get the same thing. Okay, so let me just pause there. All right, so there's a second special case we're going to be looking at, and this is a perfect square. So this is when you have a binomial multiplied by itself, or that binomial squared. So let's try again, and we're going to expand these, and we're going to see if there's a pattern that evolves. So if you have something squared, you can just write it out twice. So x plus 7 squared is just x plus 7 multiplied by itself. And then you can just FOIL that. So you'll get x squared plus 7x plus 7x again. Forgot the x. There you go. And then plus 7 times 7, so 49. One thing that we already noticed is that these numbers are identical. So we're just adding the number to itself. We'll see if that's always the case in the other examples. Okay, so 14x plus 49. Okay, so that 49 looks like it's just 7 squared. The 1x looks like it's just 1 squared, which is 1. And the 14 just looks like 7 added to itself. But what if the coefficient in front of x is not 1? Do we get a similar pattern? How is it different? So let's look at this one. So 2x plus 5. So here we're going to have 2x plus 5 multiplied by itself. Okay, so let's FOIL this. 2x times 2x is 4x squared. 2x times 5 is 10x. And then 5 times 2x, so 10x. So again, we get the same number twice. And then 5 times 5 is 25. Okay, so we get the same number twice. But in this pattern, it just sort of looked like you were just taking this number and multiplying it by 2. Right? But in this case, you're getting 20x. which is not 5 times 2. However, if you multiply both coefficients, 5 times 2 is 10, and then double it, you get 20, which would make sense here as well. 7 times 1 is 7. You double it and you get 14. So here's a pattern. Let's try this pattern in one step in this one. So the first number is just going to be the 3 times itself, so 9. We have 9x squared. The last one is going to be this number multiplied by itself. So minus 5y times minus 5y is positive. Oh, sorry. Positive 25y squared. Then our middle number, if we multiply the coefficients, so minus 5 times 3 is minus 15, and double that, minus 30, and then xy. Right? And that is what we call a perfect square. The equations are down below. We have two of them, one for when we have a positive and one for when we have a negative. Right? And later, if you like, you can even expand that by using FOIL and double check that this is actually what it expands into. I'll just take a quick pause. Okay, so to use a perfect square to factor, a perfect square is a little bit harder to recognize than a difference of squared. Because a difference of squared is a binomial. The middle term is always 0. Whereas this one, it's not. Okay? But you can try. You can look at the last one. Right? That last number should be a perfect square. So is 9 a perfect square? Yes. Right? 3 squared is 9. So maybe this is a perfect squared. The first number should also be a perfect squared. Is 1 a perfect squared? Technically, 1 squared does equal 1. So that works. But what about that negative 6? That's the trickier one. So up here, let me just go back up here. When we expanded, we noticed that 7 times 1, which is 7, and then we doubled that to get 14. Okay? 5 times 2 is 10. We doubled that, we got 20. Okay? Minus 5 times 3 is minus 15. We doubled that to give minus 30. So in this case, if we are to write this as a 1 and a 3, so if I did x and a 3, and since it's a negative in this equation up here, it would be a minus if it's a negative. Question is that true? Does that work? Well, let's try it. Let's do minus 3 times 1, which is minus 3, and double that. That gives you minus 6, which is what this is, so it does work. Again, it's hard to see that pattern. Seeing a pattern takes practice. So, I mean, if you practice it and you can see the pattern, you'll get the perfect squared, but you can also just do what we did the previous day. Look at this question and say, okay, what two numbers multiply to give you positive 9 and add to give you negative 6? You'll just say, okay, minus 3 and minus 3. Minus 3 times minus 3 gives you 9. And when you add them, you get negative 6. And so you'll have this. And then you realize, oh, they're the same bracket. That was a perfect square. And that's great, right? If you do it using the method we did yesterday, and after you do it, you realize the brackets are the same, that's a perfect squared. I can continue to simplify it like that. I'm really happy. Okay? I'm not going to force you to try and recognize it and do it in one step. Okay, but just for this lesson, we're just going to try and do it together. Okay, so let's try one more. This is where our first coefficient, z, is not 1. But is it a perfect squared? It is, right? So 5 squared is 25. All right. So far it looks like it might be a perfect squared. What about 4? Yes. 2 squared is 4. So both 25 and 4 are perfect squares. So it's possible, since this is addition, we're going to go with this formula. And I'm going to write 5y plus 2 squared. But is this true? Right? If I multiply these coefficients and double them, do I get 20? If I do, great. Then I'm right. If I don't, then this isn't a perfect squared, and since the first number is not 1, I'll probably have to go back and do decomposition to try and figure out how to factor it. But in this case, 5 times 2 is 10, and if I double 10, I get 20. So I'm good with that. So I'm going to pause it there.